Back again with another video about derivatives, but we're going to look at derivatives from a different perspective now. Before we do, I have to talk about notation a little bit. So I say, suppose that y equals f of x. Y is a function of x. Then f prime of x equals this thing, which most people, when they see it, refer to as dy dx. Anytime in calculus that you hear somebody say dy dx, they're talking about a derivative. This is another symbol for the derivative. And we have these two different symbols for derivative, partly because calculus was actually invented by two different people in different parts of the world, neither one of which had any idea that somewhere else in the world somebody else was working on exactly the same problem. So this is pretty much the notation that Isaac Newton used when he invented calculus. And this is the notation that Gottfried Leibniz used when he invented calculus. And both notations have survived down to this day. And it's not necessarily a bad thing. Each form of notation has its strengths and its weaknesses. Now, let me tell you a little bit about the motivation behind this notation. Remember what a derivative is. It's the slope of the tangent, right? The derivative is the slope of the line tangent to the graph of f of x. So we're talking about the slope of a line. And how do we compute the slope of a line? y2 minus y1 over x2 minus x1. In other words, change in y over change in x. Well, guess what? From this notation evolved the notation dy dx. This notation essentially refers to delta y over delta x with the added connotation that we're computing the limit of this thing as delta x goes to 0. So this is where we get the dy dx notation. It's a not so subtle reference to the slope of a line. In this case, the slope of the line tangent to the graph of f of x. Now, why did I need to tell you this? Because there actually is a reason that makes this conversation absolutely necessary. For lack of anything better, I'll call this a differential operator. And what do people call this thing when they see it? You guessed it. They call this thing d dx. I need to talk about this thing ddx because everything that we're about to do for the next 45 minutes or so is going to be in terms of this symbol. So we should understand what it is and what it means. Okay. This thing, ddx, is an instruction that tells us to compute the derivative of the expression that follows. And I guess I better give some 4 examples. This expression. So we look at this expression and we see the ddx and we say, oh, this is an instruction that's telling us to compute the derivative of f of x. And if that's what we think, then we're absolutely right. Let's look at another example. Given this entire expression, we consider ddx to be an instruction that tells us to compute the derivative of the expression that follows. ddx is an instruction that tells us to compute the derivative of the square root of 2x plus 1. Now, having said that, there's also another way that we can view this. So this entire expression, not just the differential operator, but this entire expression, we consider this to be the derivative of f of x. So this entire expression, we consider that to be the same as f prime of x. Now let's look at another example. This entire expression, the dx and the square root of 2x plus 1, we consider this entire expression to be the derivative of the square root of 2x plus 1. Now, by itself, we consider this operator, ddx, to be an instruction that tells us to compute the derivative of what follows. We consider the whole expression to be the derivative of square root of 2x plus 1. Now, why am I making such a big deal out of this notation? Well, we've just computed the derivatives of a few functions, and the functions weren't that complicated. Oh, by the way, just for emphasis, let me take this remark and put it down here also, or the equivalent of this remark. You see, in our last example, we actually computed the derivative of this function, didn't we? So we consider this entire expression to be the same as what the derivative of this function was when we computed it. Do you remember what it was? I'm thinking it was square root of 2x plus 1 in the denominator, 1 over square root of 2x plus 1. So we consider this entire expression to be the derivative of square root of 2x plus 1. In other words, this thing is the same as that thing. Now, why am I making such a big deal out of notation? We did a couple of examples where we computed the derivatives of functions. And when we did, I remarked at the beginning of each exercise that we only had one tool in our tool bag, and that was the definition of derivative. We had to compute the derivative of our functions using the definition of derivative. In other words, the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. That's the only tool we have in our toolbox. And for a function like f of x equals square root of 2x plus 1, it's fairly complicated. For the exercise that we did before that, and I don't remember what it was, but it was a second degree polynomial. It took us quite a bit of work to compute that derivative too. What would happen if we had to use the definition of derivative and compute the definitions of sines and cosines and tangents and more complicated functions? It's doable, but very, very complicated. So what we'd like to do is put a few more tools in our tool bag. Being able to compute the derivative using the definition is fine, and on occasion we may need to refer to the definition of derivative. But the aim of this class, this calculus class, is to use the derivative as a tool for solving more important problems. So in this class, primarily, we're using the derivative as a means to do something else. The derivative is going to be a tool to do something else. So we don't want to spend 20 or 30 minutes to compute a derivative. We want to be able to compute derivatives quickly and then apply the result to something else. And in order to do that, we're going to have to look at properties and rules and laws of derivatives. And that's what we're going to do next. And we're going to use this ddx notation copiously in our properties and rules of differentiation, or properties and rules of computing derivatives. Okay, I was about to end the lecture, but just let me say something. I have inadvertently been using the expression differentiation, and I haven't defined what that means. So in case I slip up again and use the word differentiation, let me just say this. In calculus, the word differentiation refers to the process of computing a derivative. When we compute a derivative, that's called differentiation. And the verb to differentiate means to compute a derivative. Just in case I start throwing that word differentiation around without being conscious of it. When I say differentiation or differentiate, I'm talking about computing a derivative. Okay, rules and properties of derivatives. And notice that all four of these properties are stated using the DDX notation. That's one of the reasons that I sort of beat that bit about the notation into the ground a few minutes ago. Here we have the derivative of a constant, and that's equal to 0. So the derivative of a constant is 0. The next rule is called the power rule, and it tells us how to compute the derivative of x to any power. We take the exponent and bring it down front as a multiplier, and then subtract 1 from the exponent. It's a two-step process. First step, take the exponent and bring it down front as a multiplier. Then subtract 1 from the exponent. And this seems like too much of a simple-minded process to have any chance at all of working for x to every single exponent. And yet it does work. This works for any exponent. You can put a ham sandwich in here for n, and when we compute the derivative, we're going to get a ham sandwich times x to the power of a ham sandwich minus 1. No matter what the exponent is, this is going to be the derivative. It seems too simple to work for every real number exponent, but it does. The next property. Here we have the derivative of a constant times a function. And this property says that that's equal to the constant times the derivative of the function. So the derivative of a constant times a function equals the constant times the derivative of the function. And as far as computation goes, what that tells us is that if we're computing the derivative of a constant times a function, what we can do is just write the constant down and then forget about it and compute the derivative of the function. And when we're done, we just multiply the two together. Our fourth property, we have the derivative of the sum or difference of functions. And that turns out to be the sum or difference of the derivatives. So we could say that the derivative of a sum or difference is equal to the sum or difference of the derivatives. As far as computation goes, what this is actually telling us is that if we're computing the derivative of the sum or difference of functions, we can compute the derivatives one term at a time and then just add them together. So if we're computing the derivative of the sum or difference of functions, we'll compute the derivative of the first function, then we'll compute the derivative of the second function, and so on, and then just add them together when we're done. So we're going to use those four rules to do a bunch of exercises now. But by the time we finish these exercises, we will have accomplished an incredible amount. Okay, example time. The derivative of 8. What property do you think we should use to do this? Maybe property number 1, where we compute the derivative of a constant, right? And property 1 says that the derivative of a constant is 0. So the derivative of 8 is 0. What about the derivative of negative 1/2? Well, negative 1/2 is a constant, right? And property number 1 tells us that the derivative of a constant is 0. Well, that was easy. F of x equals 11/4. So what should the derivative of f of x be? What do you think? Well, f of x is a constant, right? 11/4 is a constant. What is it? 2.75 maybe, is that it? So if f of x is a constant, what should the derivative of f of x be? Property number 1 says it should be 0, right? Okay. Y equals pi. So what about the derivative of y prime? What do we know about pi? It's approximately equal to 22/7. Decimal equivalent 3.1415 ... Pi is a constant, isn't it? So y prime is going to be 0. Derivative of a constant is 0. Okay. Y equals 15. If y is 15, then what is the derivative of y, dy dx? Y is a constant. The derivative of a constant is 0. Okay. Well, you know what? I think we have property 1 down pat right now. So we'll move on to some property 2 exercises. Onward and upward. Now we're computing the derivative of x cubed. So which of the properties over here do you think we should use? Probably this one where we're computing the derivative of x to the n, right? The power rule. And the power rule tells us that when we compute the derivative of x to the n, it's a two-step process. First of all, bring the exponent down front as a multiplier. And then secondly, subtract 1 from the exponent. Now, let me see if I can do that. Bring the exponent down front as a multiplier, and then subtract 1 from the exponent. Wow, that's easy. That is so easy, even I can do it. Okay? Another example. X to the power of 10. It's a power rule problem. 2 steps. First step, bring the exponent down front as a multiplier. Second step, subtract 1 from the exponent. Now that we got the hang of this, I think we can apply the power rule in 1 step. Let's see. We can go essentially from here to here. So what do? First step, bring the exponent down front as a multiplier. Second step, subtract 1 from the exponent. 5 minus 1 is 4. Okay. There's our derivative. Well, wait a minute now. Should that work for negative exponents? Earlier on, I did say that this power rule would work even if the exponent were a ham sandwich, right? If it'll work for a ham sandwich, it'll work for a negative exponent. And we do it exactly the same way. Bring the exponent down front as a multiplier, and then subtract 1 from the exponent. So negative 2 minus 1, negative 3. This really is so easy that even I can do it. Let's do some more examples. F of x is x to the 20th. So what's the derivative of f of x? Well, it's the derivative of x to the 20th, right? Power rule problem. Bring the exponent down front, subtract 1 from the exponent. Wow, that was easy. Y equals x to the 8th. So what would the derivative of y be? It's a power rule problem, right? So bring the exponent down front as a multiplier, and then subtract 1 from the exponent. Y equals x squared. So what's the derivative of y? It's a power rule problem. So bring the exponent down front as a multiplier, and then subtract 1 from the exponent. And x to the 1, unless we have a reason to draw attention to the fact that the exponent is 1, we usually don't write it. So we'll probably just write this as 2x. Although there's nothing wrong with that. There's nothing wrong with saying x to the first. Okay, let's see. Some more examples. I have an ulterior motive for this one. Although maybe in the last example I sort of tipped my hand. How am I going to do that? The derivative of x. Well, let's see. I could use the power rule problem, or the power rule property, if I had it written as x to a power, right? So this is really the derivative of x to the first. And it is a power rule problem. Bring the exponent down front as a multiplier, then subtract 1 from the exponent. And we get 1. Now, if you're like me, you'll remember this until we take a test. And if you're like me, everything seems fine when you take a test until you start and you go to write your name and you can't remember your name. Sometimes this happens when we take a test. So what I'm going to do is I'm going to call attention to what it is that we've just demonstrated. The derivative of x is 1. Based on what we just did here, it's obvious. And if we did not draw special attention to this property, then we could always derive this fact the way we did up here. And we could probably do that with no problem, except when we sit down to take a test, and then we don't even know what our name is. So, just so that we make ourselves aware of this right now, this is a special case of the power rule, where the exponent happens to be 1. The derivative of x is 1. So we'll remember that. The derivative of x is 1. Now, let me do another exercise, kind of a special exercise. The derivative of the square root of x. Now, which one of these properties over here are we going to use so that we can compute the derivative of the square root of x? Which one of these properties? And we look at them and we say, well, I don't really see anything over here that looks like that. So I guess in order to use one of these properties, we're going to have to rewrite this in a different form. What's another way of writing the square root of x? By the way, this is one of my favorite words in math, rewrite. So the derivative of square root of x is the same thing as the derivative of, what did you say? How can we rewrite this? maybe write this as x to the power of 1/2. They are the same. And now we're computing the derivative of x raised to a power. So we get to use our power rule. The power rule says bring the exponent down front as a constant multiplier, then subtract 1 from the exponent, this is how we compute the derivative of x to the derivative of square root of x. We rewrite it as x to a power, and then we do the power rule. So whenever we see derivative of square root of x, write it as derivative of x to the 1/2. Exponents in general are easier to work with than radicals, and this is definitely one of those cases. Okay, time to move on. Okay, we're sort of increasing in complexity step by step. The derivative of 6x to the 4th. Now, can we use the power rule right away? I'm not so sure that we can, because the power rule tells us how to compute the derivative of x to the n. There's no constant multiplier out here in front. And the power rule doesn't tell us what to do when there's a constant coefficient out in front. But property number 3 tells us what to do. Property number 3 says that if we're computing the derivative of a constant times a function, then write the constant down and then compute the derivative of the function and multiply them together. So property number 3 says write the constant down and then forget about the constant and just compute the derivative of the function that follows. Let's try that again. Again, we have the derivative of a constant times a function. And property number 3 says that when we compute the derivative of a constant times a function, what we do is we write down the constant and then we forget about it and we concentrate on computing the derivative of the function. And when we do, we just multiply them together. So first step, write down the constant. And then for the time being, we'll forget about the constant. And we'll look at the function and compute its derivative. The derivative of x to the 5th is 5x to the 4th. And then we can multiply this junk out and get 40x to the 4th. And about now, some of us are scratching our heads and saying, wait a minute now, I see a pattern. And those of us who don't see the pattern, surely if we did another example, everybody would see it. So there are those of us who see the pattern and those of us who are on the verge of seeing the pattern. And here's the pattern. We look at it and we say, we had a constant times x to a power. And what we ended up doing was taking the power times the constant and then subtracting 1 from the exponent. We say, all we did was we brought the 4 down and multiplied it by the constant in front to get 24. Then we subtracted 1 from the exponent to get x cubed. Well, does that work? Let's look at this one. We bring the exponent down and multiply it by the constant out front. 5 times 8 is 40. And then we subtract 1 from the exponent. Ooh, that's 4. Okay, that's exactly what we do. Now, the reason I don't tell everybody to continue doing the derivative of a constant times x to a power this way is because everybody on earth who does calculus does this operation the same way. Let's look at derivative of 6x to the 5th. What do? We bring the exponent down and multiply it by the constant in front. 5 times 6 is 30. And then we subtract 1 from the exponent. 5 minus 1 is 4, and we're done. I might be inclined to tell you to do it otherwise and tell you to do the operation this way, but the fact of the matter is, every single person on earth who does calculus, when they compute the derivative of a constant times x to a power, they do it exactly the same way. And this is how they do it. They bring the exponent down front and multiply it by the constant. That's 30. And then they subtract 1 from the exponent. That's 4. It's sort of like something that all of us know intuitively. There are 2 buildings on campus, and there are sidewalks that pass by each building. So what are we going to do? Even if people tell us to walk on the sidewalk, are we going to go out this building and along the sidewalk and over here to that building? No. Everybody intuitively knows that the way you do it is you start here and you go here. Why? Because up to a certain point, our brains are all hardwired the same way. And we say, you know what? I'm not going to go along this leg of a right triangle and then this leg of a right triangle to get to here. I'm just going to go along the hypotenuse. It's a shorter distance. Intuitively, we all know that. And intuitively, our brains are all hardwired the same way when we compute the derivative of a constant times x to a power. Everybody on earth does it the same way. And if we're not doing it that way yet, in about 2 minutes we will be, because our brains are all hardwired the same. We're going to look at this and say, oh, bring the exponent down and multiply it by the 6, and that gives us 30. Then subtract 1 from the exponent, that gives us x to the 4th. Everybody on earth does it that way, so from now on, that's how we're going to do it. So a few more exercises. Now remember what we do? We bring the exponent down front and multiply it by the constant. So 4 times a half is 2. And then what do? We subtract 1 from the exponent and get x cubed. Let's try another one. What do you think? Bring the exponent down front and multiply it by the constant. So we have negative 3 times 8 is negative 24. And then we subtract 1 from the exponent. Okay, another one. Oops, I didn't want that. Derivative of 2 square root of x. Now we do have to do something here. I don't like radicals, so I gladly rewrite the square root of x as x to the 1/2. Besides, this word is one of my favorite words. Rewrite. Okay, how are we going to do this? Bring the exponent down front and multiply it by the constant. So we'll have 1/2 times 2 is 1. And then what? Subtract 1 from the exponent. There we go. We are gaining by leaps and bounds. Well, let's see. Let me interject something before we go on to the next point. Suppose we compute the derivative of a constant times x. What this really is the derivative of the constant k times x to the first power. And we use the power rule. We bring the exponent down front and multiply it by the constant. So we have 1 times k is k. And then we subtract 1 from the exponent. So we'll have x to the 0. But x to the 0 is what? 1. So this is just k. So we might list this as a special case also. The derivative of a constant times x is just the constant. So let's do an example. The derivative of 3x, well, this is a constant, right? So it's the derivative of a constant times x, which will just be the constant. And then another example, derivative of pi x. Well, pi is a constant, isn't it? So we have the derivative of a constant times x. That's just the constant. So I wanted to bring this special case to our attention because whenever we see this, even though we could use the power rule, typically we don't. We just say the derivative of a constant times x is the constant. Okay, here's a good one. This is a little bit more complicated than the others. What property do we need to use here? What I see here is the derivative of the sum or difference of functions. And property number 4 tells us how to handle that. Property number 4 says that when we compute the sum or derivative of functions, we can compute the derivative of each term separately and just add them together. In other words, compute the derivative of the first term, compute the derivative of the second term, and so forth, and then just add them together when we're done. So let's apply that to this exercise. Compute the derivative of the first term. So 5 times 8 is 40. Subtract 1 from the exponent. Move on to the next term. Bring the exponent down. 2 times negative 6 is negative 12. Subtract 1 from the exponent, so that's just x to the first. Derivative of 3x, that's a constant times x, so the derivative is just the constant 3. And 2, that's a constant. What's the derivative of a constant again? 0, that's right. Plus 0. So this is our answer. Well, that wasn't hard. Let's do another one. Because I see a square root there, and I hate radicals, before I attempt to compute any of this derivative, I'm going to use one of my favorite words in the whole English language. Rewrite. Okay. Now I have my function in the form that I wanted it. And since it's the derivative of the sum or difference of functions, I can compute the derivative one term at a time. The derivative of the first term. Bring the exponent down, and we have 3 times negative 9 is negative 27. Subtract 1 from the exponent, x squared. Move on to the next term. Bring the exponent down front. We have 2 times 2 is 4. Subtract 1 from the exponent, so we have x to the first. Move on to the next term. Bring the exponent down front. We have 1/2 times 5, so that's 5/2. Subtract 1 from the exponent. That's x to the negative 1/2. Move on to the next term. The derivative of 8 is a constant, so its derivative is, what's the derivative of a constant? 0 plus 0. So this is our derivative. So what we've learned how to do so far is compute the derivative of any polynomial plus a little bit more than that. Before we go, I'm going to add 2 properties to our list. I'm going to add number 5 and number 6. 2 more rules or properties of derivatives. The derivative of sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. So let's look at an example. It's the sum or difference of functions. So we can compute this derivative one term at a time. When we compute the derivative of the first term, we see that it's a constant times a function. And property number 3 says that when we compute the derivative of a constant times a function, we write the constant down, then compute the derivative of the function, and then multiply them together. So that's what we're going to do. I'm going to write the constant down, then I'm going to compute the derivative of sine of x, which is cosine of x. I'm done. Now I move on. I have the derivative of -8 cosine of x. It's a constant times a function. And to compute the derivative of a constant times a function, I write the constant down, and then I compute the derivative of the function. So I wrote the constant down, -8, and then I write down the derivative of cosine of x, which is negative sine of x. So what I get is 3 cosine of x plus 8 sine of x. That's my derivative. Well, give yourselves a pat on the back because we've accomplished quite a bit in this session. And I'm going to give you some homework so that we can put it to use immediately. But see, before we started this lecture, we had 1 tool in our tool bag. Now we've got 6, and in a little while, a day or two, we'll add a few more tools. Don't worry, you won't get overwhelmed. We'll add them a few at a time so that we'll be able to assimilate all of this.